All right, welcome to part 2 of today's lecture, where we're going to be going, in this one, we're going to talk about the conservation of momentum. Yes, only in one direction. So in the last video, we saw that momentum and impulse were derived from Newton's second law of motion, which said that a force causes an acceleration, a net force causes an acceleration, and that acceleration results in a change in velocity. Well, it turns out that the conservation of momentum comes from Newton's third law of motion, which again states that forces come in equal in magnitude, opposite in direction, and every force comes in an action-reaction pair. So here we have two balls that are coming towards each other. Now we'll talk about this notation in a little bit. It gets pretty busy, and we'll talk about how we can ignore some of the subscripts as we move on into problem solving, but this is the notation the textbook is going to use. We have the initial velocity in the x direction for object 1, and we have the initial velocity of the x direction for object 2. Now these two are going to hit each other with an action-reaction pair according to Newton's third law. So the force that ball 1 experiences from ball 2 is equal in magnitude but opposite in direction for the force that ball 2 experiences from ball 1. And then after the collision, in this particular instance, the two balls move away from each other afterwards with final velocity for 1 and the final velocity for 2. So we're going to skip the proof. If you want to check it out, it's in section 2 of chapter 11. But this is what the proof looks like. Why these parentheses are so much bigger than the ones on the right, it's a great mystery to me. But we have the final momentum for 1 plus the final momentum for 2 is equal to the initial momentum for 1 plus the initial momentum for 2. And again, there are a lot of subscripts that are given to this. So something that you, if we take this to multiple dimensions, we just have the total momentum for 1 plus the total momentum for 2, both of these being final, equal to the initial value. Now, a very common way that you will see other textbooks or other notations used is instead of using I and F, the I is just dropped and it's never included anywhere. And then for final, the prime notation is used. So this little tick mark is given up here because it is changed. So this notation helps us get rid of one of our subscripts, as we don't have to include I and F. Being 100% honest with you, I know I've been trying my best to stick to textbook notation. I hate writing out 3 subscripts every single letter. I like the prime notation because it eliminates I, and I don't have to do F, I just have a little tick mark. It's a little bit easier to do. So I am going to be using this little prime notation here. I'll still use X and I'll still use numbers for the different objects. However, I'm going to use prime for F and nothing for I. So also with what you may see in other textbooks is instead of using numbers for the objects, they use letters. So it would be A and B instead of 1 and 2. But that's usually a pretty straightforward swap between the textbooks. So what if we have, so what if we have more than 2 objects? Sorry, that question was just really looking at it and my brain just for some reason couldn't read that. So what if we have more than 2 objects is really what this is. Well, then we'd have to consider the total momentum before and the total momentum after. So total momentum is given a capital P. Again, we have the vector over it because momentum is a vector, and we literally just add all of the values together Here, when using the sum notation, a K is used because we don't want to confuse it with I for initial. That's all that's different with how it is typically represented. So just add. If you have 2, you have just 2 values. If you have 5, for some reason, you just have 5 values. It's just adding them all up together. And that means that if we wanted to relate the total momentum to the forces, basically we have the total change in momentum divided by the change in time, and that's going to be equal to the net force being done on the system. Now, typically in this textbook, the most objects you are going to be dealing with is 3. So you don't really need to worry about that. And when you're dealing with the 3 objects, we put them all within the system, so we don't have an external force. So we are not going to be using this in this class, but I wanted to show it because the textbook's going to keep talking about using this equation. So this is if we have, more than 2 objects, which is possible. You can have multiple objects colliding at once. That is a valid thing to have happen. So let's focus on what we are typically going to be dealing with in this class, which is going to be an isolated system. So as with energy, an isolated system means we have no external forces. Every force we deal with is going to be internally based. So it's going to be the 2 objects colliding with each other. And in that case, the momentum of an isolated system is not going to change. And this is where we get the law of the conservation of momentum in its more formal definition. So when we were looking at it on the first real slide of this video, it was just kind of like, oh, it comes from the 3rd law, here's what it is. We also can look at it in terms of no external forces. And that means that the total momentum before is going to be equal to the total momentum afterwards. And we can use that in writing out the momentum of however many of objects 1 to whatever number we have before is equal to the after momentum for the collision. And because momentum happens to be a vector, we can treat the directions separately. So we can look at x and do all the x stuff. We can do y and we'll do all the y stuff. And if we, for some reason, had a 3rd direction, we could do z by itself as well. And this is something we are going to explore when we look at multi-dimension conservation of momentum. But today we're only dealing with the 1 direction. So the system is again important based on this definition. The textbook gives us the systems, so we'll be good in that case. So here we have the problem-solving strategy for conservation of momentum. So it says, if possible, choose a system that's isolated. Again, the textbook is going to be giving us these systems where either it explicitly tells us the external force or we already have a net force equal to 0. So because of that, we probably don't have to do this second step. Pictures are going to be very important, as per usual, for this type of question, because it helps us establish directions that things are going to be pointing and moving. So with that, we then can have the conservation of momentum in the x direction and y direction separately. In this lecture, we're only going to be dealing with 1 direction. And then see if your answer is reasonable. It's a little hard to judge that if you don't know what the answer is supposed to look like in the first place, in my opinion. But, if you feel like the answer shouldn't be 0.000003, then maybe check your math. So this is an example from another textbook. Let's just go ahead and work through this one. So here we have a boat. There's a child in the boat, and there is going to be a package that they are going to throw out of the boat. So this is our before picture, and then we have the after picture, and let's just pretend this is what has been done. So in each case, we have some masses given to us and some information. So let's go ahead and let's come up with some subscripts. So for the child, I'm going to have it as C. The boat is going to be B. And the package I'm going to have as P. Just because I don't want to use B for box because I already have B for boat. So the mass of my child is given as 24 kilograms. The mass of my boat is given as 35 kilograms, and the mass of my package is 5.7 kilograms. Now, based on the pictures I've drawn, I should probably give myself a coordinate system because, again, momentum and velocity being vectors, direction matters. So I'm going to say that positive x is to the right, and that's going to apply for both my before and after case. I'm going to call this one before, this one after. So here it tells us that everything was initially at rest. So my initial value for the velocity for both the child, the boat, and the package is all going to be at rest because they are all, the child and the package are in the boat, and we are being told that the boat is at rest. Now after, we don't know the velocity of the boat, and that's what we're looking for. We have the velocity of the package is because of the direction we've chosen, it's going to be 10 meters per second, and it's going to be positive. Now, when we think about this, we need to think about where the child is. Now, last I checked, this question doesn't tell us that the child falls out of the boat. So that means that the child is still in the boat. So I'm going to have the final velocity that I'm looking for. It's not just the velocity of the boat, but it's the velocity of the child as well, because they are moving together. We could make it, if we wanted to, say that the boat had a lever arm instead of a child, and just it shoots it, it catapults it off, and then we just have a heavier boat. We could replace the child with that, with a catapult of some sort, and then have it be part of the boat. In this case, we don't have that. We have the child physically throwing the package, but the child stays in the boat, so they move together. So let's set up the conservation of momentum. So we're going to have the mass of the child and times the initial velocity of the child. We have the mass of the boat times the initial velocity of the boat, plus the mass of the package times the initial velocity of the package. This is going to be equal to the mass child of the boat afterwards. Mass of the child times the velocity of the boat afterwards, plus mass of the boat times the velocity of the child boat system after, plus mass of the package times the velocity of the package after. So here I've used these subscripts to tell me which object it is. It's equally valid to label them 1, 2, 3. Whichever one you want to use. Letters in this case make a little bit more sense to me personally, because then I know I'm using the right mass, because I know C stands for child more so than the number 1 stands for child. Right, so that is why I'm using letters in this one. In the example for the next video, I will be using numbers so you can see how that's done there, but it's the same idea. So the question tells us that initially all of our objects are at rest. And because the child and the boat move together, I can rewrite my equation on the right side as such. So I am solving for the final velocity of the child and the boat that are moving together. So rearranging, CB. Again, I'm using this little prime thing here to indicate the final value. So I have the final velocity of the child in the boat, because the child is in the boat, is going to be equal to the mass of the package times the velocity of the package divided by the mass of the child plus the mass of the boat. However, I subtracted this to the other. I subtracted my momentum of the package to the other side, so I need this negative sign here. When we are doing conservation of momentum, we are always adding our momentums together. It's when we plug in the numerical values that we will account for the direction of our object. So here, I'm assuming that, I'm adding all my momentums together, because that is what the conservation of momentum states. I add every momentum I have together. Somehow, these are going to have to add up to be equal to 0, but I don't know which one is negative. So I add everything together. When I rearrange, a negative sign pops up, which is good. And then when I plug in the values, I need to make sure I plug them in based on the coordinate system I have. So mass is always going to be positive, so I don't need to worry about that one. So I have mass of my package, which was 5.7 kilograms, times the 10 meters per second. Here my 10 is positive because I said that to the right was positive. If I threw the package to the left, I would plug in negative 10 meters per second. If I said to the right was negative x, I would plug in negative 10 meters per second in that case. And then I'd have a negative times a negative giving me a positive, which would indicate the boat moves in the opposite direction of my package. So again, picture is important because it gives us a coordinate system, which in turn helps us figure out which direction objects move relative to each other. So then I need to divide by the mass of the child, which was 24 kilograms, plus the mass of my boat, which was 35 kilograms. Taking this in and plugging it in, I got negative 0.9661 meters per second. In this textbook, it was 3 sig figs, so negative 0.966 meters per second would be our answer. So for this question and for all conservation of momentum, we need to make sure that we are adding our momentums together. And it's once we do the algebra and plug in our velocities based on the coordinate system we've determined or the coordinate system we were given, once we do that, the correct direction of our velocity should pop out for the object. So again, it's when you plug in numbers that we should account for the sign of our particular velocity value. So here, by having a negative almost 1 meter per second, we are saying that the boat and the child would move to the left. If we went through and plugged this into our equation, this should all add up to be 0 or 0.000 something. So we could go through and check and make sure that we did algebra right. In this case, the algebra wasn't particularly complicated, so I think I'm confident with this. So I'm not going to show you checking this, but by having the negative, I at least have a chance for my positive value to be canceled out to be 0. All right, so that's going to wrap it up for this video. Make sure to watch the next video as well.